So good morning. I wanted to just start off giving you a few context tokens about myself. So I am an academic little brother of Alan Edelman, one of the Julia founders. And our advisor, Nick Trefethen, loves to brag that he was literally MATLAB customer number one. And he has the framed receipt to prove it. So we were both immersed in MATLAB from the very start of our training, to the point where when I was still a graduate student, in 1995, I went to a MATLAB conference, and by an incredible coincidence, I ended up playing a game of MATLAB Jeopardy and excelling at it, doing really well at it, and got a job interview because of it. Um, the first, so then I went ahead and then wrote a lot of books using MATLAB and packages using MATLAB and things about MATLAB. The first version of Julia I downloaded was 0.3, and I played around with it. I said, well, this is cute, but now it's time to get back to work. Um, but I kept downloading new versions when they would come out. Sometime around version 1.3 or 1.4, I experienced an inflection point where suddenly I preferred working with Julia over MATLAB. And so now, 30 years removed from playing MATLAB Jeopardy, here I am at a Julia conference, so I'm very pleased to be here. Why did I write a package on rational function interpolation? So the approximation of functions is a foundational part of scientific computing. And one of the most common settings for that is interpolation, right? So I have some values at a finite collection of nodes, and I want to find a function that goes through those nodes. Of course, there's a lot of different ways you could do that, right? So the question becomes, how do you choose how to do this? And accordingly, if you do a very cursory search for packages or for interpolation on Julia packages, you get a long list. You have to screen out some things about string interpolation, but this is just a very subjective subset of what comes up. So why add to this, right? So let me give you an example of two functions, tangent and the inverse tangent. So if you look at them from the interval -1 to 1, they both look pretty nice, right? In fact, they're analytic on those intervals. But we know that if you extend the tangent function out a little ways, then you're going to encounter a singularity, right? So you should not be surprised to find that that singularity could influence the convergence rate of something like a polynomial approximation, because polynomials don't have singularities. So that's an argument for using a rational function instead, because rational functions can have singularities, poles in particular. Now with arctangent, you can extend that as far as you want. It's still analytic, so that seems like a different situation. But that's wrong, because the right way of looking at these things is in the complex plane. So in these plots, the original interpolation interval from -1 to 1 is the black line. And you can see that we have a pole over here, because if you look at red, green, blue, it's going clockwise around that point, right? The 0 here in the middle, if you go red, green, blue, is counterclockwise. So you know that's a 0 instead. So the coloring here, the hue is the phase of the complex number on a cyclical color map. And the lightness cycles from dark to light for each power of E. So there we see the poles that we already knew about just by going in the real direction. But now we see that arctangent is really not that different, because it has branch points out at plus or minus I. In fact, you could argue that these are worse, because as you can see, right, the function is going to have a jump across the branch cut. And so this is another case where polynomials are going to feel the effect of those singularities, particularly as they become closer and closer to the interval. So let me back that up with some computations. So I'll say more about what's going on here later, but let's say I come up with a bunch of 500 test points from -1 to 1 on the interval, and then I define a function here that I'm going to use after the fact to check the error in the approximation. So here's the tangent from -1 to 1, and we see the singularities hanging out outside. So this is from the rational interpolation package, the function approximate. So I'm approximating f at that collection of points. And what comes out is a degree 8 approximation, right? So degree 8 upstairs and degree 8 downstairs. So that would be 9 plus 9 equals 18. But then there's a redundancy because you can divide through by one coefficient. So there's only 17 coefficients there. Here I've got a polynomial interpolant from the approxfun package, and it uses degree 36. So 37 coefficients. Okay, so degree 8 plus 8, 8 and 36. Now, if I change the scaling in x, I can move those poles closer to the approximation interval. The rational interpolant wasn't affected. It's still degree 8, 8, because that's just a pole sitting there. Chebyshev interpolant went up to degree 74. And I can keep playing this game, so if I move them a little closer, okay, now it feels those a little bit more. It had to go up to 10, 10, but the polynomial interpolant had to go up to degree 128. And so we can be a lot more efficient with a rational function in this case. Looking at the arctangent function. Now the singularities are on the imaginary axis. Degree 12, 12 versus degree 38. So 12 and 38. If I then move them 10 times closer. Now these are more genuine, more serious singularities, so more work is needed. So I went from 12 to 46, but the degree went up by a factor of almost 10 to 324. And if I go up another factor of 10, the degree of the rational went up just a little bit, and I got almost another factor of 10, so I'm degree 3000 for the polynomial now. So that's a motivation for using rational functions as approximations. How's it done? Well, probably when I say the word rational function, this is the thing that you think of: ratio of two polynomials written in monomial form. The moment you conceive of these things this way, you've lost the game. Okay, at least computationally speaking, you don't want to do that. There's a much better representation, which is the barycentric formula. So you can see that this too is a rational function if you just clear out the denominators, right? But it's one that's a much more stable and useful form. So I'll go into some more details about that on the next slide. There's another form, which is a continued fraction. And that also turns out to be computationally useful, which was discovered just last year. So I'll get into that a little bit later as well. There's another useful representation, which is a partial fraction expansion. That is in the package. It's not as well developed yet, and it's got some things I want to do with it in the future. So in the interest of time, I'm not mentioning that today. So let me start with this barycentric formula. It's designed so that if the zk's are my nodes, then the yk's are values of the nodes. Because imagine if z is extremely close to z1, right? Then the only term that matters in the sums is k equals 1. And everything cancels out except for y1. So if I have a function I want to approximate, then what I should do is let yk be f at zk, because then r will interpolate it at those points. So the interpolation is just baked into this formula. Now these w's are called the weights. And for any value of the weights, I have this interpolation property. You may know, if you're familiar with the barycentric formula, there's a way to choose the weights so that this is actually the interpolating polynomial. That's actually a very simple derivation from the Lagrange interpolation formula. But I don't want to use the weights that way. I want to keep the interpolation and do something different. So instead of using them to get a polynomial, which can't have singularities, I want to use them to minimize the difference between r and f at a bunch of test points. If I try to solve that problem directly, it's pretty hard. It's very nonlinear. So what we do is linearize that problem instead by clearing out the denominator. And once you do that, you can pose this problem using linear algebra. This L here is known as a Loebner matrix. You notice that in the barycentric formula, everything is invariant with respect to a scaling of the weights. So I might as well let the weights have norm equal to 1. So I get this nice constraint problem. And now this constraint least squares problem is in fact finding the least significant singular vector of L. So that's the foundation of the AAA algorithm. You start with a set, let's say you have a set of n nodes and m test points. You can use an SVD to compute the weights. Now you have an interpolant that does a good job of approximation at the test points. You figure out what the residual actually is at the test points and choose the test point where it is the worst. And then you just greedily add that to your node set and repeat. So prior to the AAA algorithm, I don't think it's a controversial thing to say that computation with rational functions was a pretty niche idea, wasn't going anywhere. After the publication of AAA, uh, things have gotten really interesting. And so there's a lot of applications emerging now from the ability, once people realize you actually can compute reasonably well with these things. Now, I could continue this example here even up to the arctangent of 1000x. But if you're watching very carefully, you realize I'm conning you, right? So it says I've got an accuracy of 13 digits here with an approximation of degree 6969. And yet my test set, right, has a spacing of 2 over 500. Compare that to the fact that things are happening on a scale of 1 over 1000 here. Okay, there's no way that these test points, right? The test points are basically just seeing this almost as a discontinuous jump. Now, I could, let me expose that by changing my checking function here. So this does not affect the algorithm, it just affects the measurement of the error after the effect. And we see that this approximation is nonsense. It's not that good. Now, I could change the test points to have, this denser set, and it would do better. But then I'm resolving things everywhere, which is kind of silly given that it's flat almost everywhere. It's long been known that you could have the nodes approach the singularity exponentially, and that would restore very efficient convergence. Of course, you'd have to know in advance where that singularity was. So to address the situation, last year I joined up with Yuji and Nick Trefethen to write a paper in which we described a continuum version of the AAA algorithm. Very simple. So if the blue dots are your nodes and the hash marks are your test points, let's say that happens to be the worst test point that you're going to add to the node set. So it becomes a node, and then you just subdivide in that neighborhood to get new test points. So by repeating this over and over, we can exponentially approach a singularity, and it discovers the singularities naturally. So that's part of the package as well. So instead of approximating on those test nodes, I can just approximate on the unit interval. Now, it's not getting full 16 digits. There is a condition number here. It's kind of interesting. But now it's doing a reasonable job with no greater degree, actually. It's doing 12 digits of accuracy compared to a degree 28,000 for a polynomial. And if we look at where the nodes are, we see that they are starting to get exponentially spaced near the origin where that singularity is. Okay, so I mentioned the continued fraction earlier. So this continued fraction idea has been known for a long time. Um, Going back, I think it's about 100 years. I haven't actually found the original publication date, but a Danish polymath called Thiele showed that if you have this simple inverse divided difference iteration, then the continued fraction expansion that you see here, right, has these W numbers in it. If the W's are defined this way, then that continued fraction will interpolate and give you f of zk at each zk from 1 to n. So this kind of just sat around. It was known to a lot of people. And there was some work with it in the symbolic math community. But if you know anything about divided differences, they're numerically very unstable. Or the best that you can say about them is their stability is highly dependent on where the nodes are and the order in which you select them. And so people have rules for trying to figure out the best way to select them. Um, they didn't, they worked okay in some circumstances. But then last year, um, Oliver Salazar Celis showed that if you use the same greedy strategy, so you have a bunch of test points, choose the worst one and make that your next node, it really seems to stabilize this process. Now, he has arguments about it. I don't think they constitute a proof just yet of that stability. Um, I have a student looking into just how stable this is and a bunch of examples at least, so we can start to get our heads around it. But it's clearly working quite well. And what's really exciting about it is that this process here is just an order n iteration. So if I have n nodes and I want to add one, it's order n. If I want to build up to a set of n nodes, it's order n squared. AAA, each step is an SVD, which is essentially order n cubed. And to build up to n nodes is order n to the fourth. So I don't know a lot of n to the fourth algorithms that are in everyday use. Now, n is often quite small, and objectively it's fast. Um, but the idea that we have a truly faster algorithm potentially is very exciting. So that's implemented as well, both in the discrete form and the continuum form. The continuum form is new as far as I know. So here again is arctangent of 100x. And so you can see timing comparisons seem to be getting a factor of speed up of a factor of about 8. So that was for degree around 45, I believe. So n is not that big, right? N's 45, and we're already seeing a nice speed up. So the potential is there maybe for doing a lot more than we could do before. Okay, so what does the package actually offer? So it's actually pretty small. The centerpiece is the notion of an abstract rational function, which has a bunch of definitions that are mostly just stubs to be implemented as an interface, essentially, of things that a rational function ought to be able to do or tell you. And then subtyped off of that is an abstract rational interpolant, which adds on the idea of having nodes and values at the nodes. So then there are types for barycentric form and for the Tila form that are subtyped off of there. So they're concrete implementations of these methods. You can construct those directly if you have a fixed set of nodes and values, or in the case of barycentric, you also have a set of test points that you want to specify. If you just want a one-off construction, you can do that. But to use these in an iterative fashion to build up a node set, you use this function approximate. So approximate requires two things from you. It requires data and a domain. Um, the data, actually, I didn't put it here. The data can be offered as a function. It can also be a discrete set of values if you have a discrete domain. But think of it as a function. I want to then specify the domain as a vector of test points. That would be the discrete case. Or if I wanted to work in the continuum mode, you specify a complex curve or path or a region. That's done using a package called complex regions that I wrote a few years ago. And this thing returns an approximation. So the approximation has the original function so that you can do some diagnostics and the original domain, the rational interpolant that it found, a notion of what poles are allowed, and I'll say something about that in a second, and then some information about how it arrived at the rational interpolant. So my thinking here is that I want a package that um, is both useful just as a library. If you just want to construct these approximations and work with them, you can do that. I think it's pretty efficient. But also the information is there if you want to study them, because these things are really new, especially the continued fraction case. And there's a lot of research yet to be done on how they work. So on this matter of allowed poles, here's an example of a function that has infinitely many poles in the unit disk, but it's analytic outside. So if I specify the domain as the unit disk, I am telling the system that I want an approximation that's analytic there. And basically it says, good luck. So um, the red dots here indicate the presence of a pole that's not allowed, because the only way of approximating this function is to put poles in there. The only approximation that was valid in the whole process was a constant. Okay, so that gold thing is the one that was returned. That's the only one that's safe. So that's not the way we probably should have done this problem, right? So instead, I want a function which is analytic in the exterior of the unit circle. And now it makes the same exact computation, but we view it differently. Now we like it, okay? Because that thing is analytic in the exterior of the unit circle. So my approximation can be as well. Now, it's only really discretizing the boundary of that domain because this is complex analysis, right? If I don't care one way or the other, I could just say to allow everything. And now the dots are neither blue nor red. They're just black to indicate, I don't know, right? This is what you wanted. Let me just finish up with a few more fun little demos of things that you can do with regions in the complex plane. So here's an approximation to the zeta function in a rectangle in the complex plane. Just for fun, I use the Thiele method. So this is the world's worst Riemann hypothesis checker. Okay, but it's fun to see, right? It's fun to see this function. And so if I look at the zeros of this um, approximation, they all have real part equal to 1/2. So I don't have anything exciting to announce on that front today, uh, but it's fun. Here's an example of a disconnected domain. So let's say I want a function which is -1 on the yellow square and +1 on the blue circle. Now, I can't do this in continuum mode yet. I haven't thought about the right way to represent that structure. So I'm running this in discrete mode, but I go ahead and approximate that sine function. And these are the poles that you get as a result. So you get this nice boundary between them. Now, there's a little bit of a worry about these poles that are in the boundary of my region, right? However, if we take a closer look, so let's look for the ones that have a real part of -3, which is where that square is. So that's these two guys here. They have residues that are essentially 0. So this comes up a lot in rational approximation. They're known as Froissart doublets, right? You have a root in the denominator and one in the numerator that cancels it out. They're kind of an annoyance. They're an inefficiency, clearly. But for the most part, they don't do a lot of harm as long as you're aware of them. And so here's a visualization of that function. So you can see it's nearly constant, not just on those two things, but in large areas of the complex plane as well. And if I evaluate R on the actual domain, um, then you see the values are all approximately either +1, right, or -1. So it was successful. Finally, here's a case of a function which is designed to have this branch cut in the right half plane, but it's analytic in the left half plane. So a lot of problems, you might want to have something happening in a half plane. So it's a little tricky to discretize the boundary of something infinite like the imaginary axis. Um, but it's child's play to transplant this problem to a finite domain. So this is also built into complex regions. So I can create a Mobius transformation that maps the unit circle to the imaginary axis. I don't particularly care which one, as long as it does that. And then I can compose the original function with that Mobius transformation. So now my problem is on the unit disk, but f is evaluated on its native domain. On the disk, then I get the branch cut sitting out here. Or if I wanted to then do this back in the original domain, I can compose with the inverse of the Mobius transformation, and now I'm back on the left half plane. Okay, so I'll leave the rest of the time for questions, and thank you, and just make a silent plug for my textbook. Okay, thank you, Movie. Any questions? Yeah.
NMBHGN.
Hi, thanks for the talk. I was wondering, is it also possible to give derivative constraints at some node of the nodes?
So currently there is no way to specify derivative constraints. I've only recently added the ability to just compute derivatives of these objects. And there's something going on there. I'm not convinced that it's numerically stable in the vicinity of a node. So these formulas exist for the derivatives, but I don't know much about them yet. So I'm not close to offering that at this point.
Okay, thank you.
Uh, Quick question. You said that when they run this AAA algorithm, it scales like n to the fourth. Has there been any attempts to improve this, or is the speed like not really an issue? Like they're doing an SVD at every step, but they only need the minimum. You can imagine, okay, you do something like land shows, you restart, you keep track of the minimal things from the previous step, you
Ab-
carry it with you,
yeah.
you convert what you're doing your SVD of to something that probably has some hierarchical structure, maybe a
Yeah,
little bit, and you
it's
could see
even
that number going down
it's even
quickly.
simpler because you can think of it as just a an updating problem
Yeah.
on the Loebner matrix. Um, there are some SVD updating algorithms out there. Um, I think it's been looked at a little bit, but there hasn't been a lot of motivation because, when the thing is operating in a tenth of a second already, unless you're doing a million of them, you probably don't care. So there hasn't been a lot of impetus to try it. I wouldn't be surprised if there's something faster, but I'm not sure you're going to get below n cubed if you do that. Maybe, but I'm not sure.
But there's hasn't been, like, any need yet. You
I don't think
haven't
there's been a
seen
systematic one,
large
but I
scale things where they really Gotcha.
yeah.
Okay.
I have a question. Sometimes you use approximations in order to compute functions faster, and polynomials have this use multiply, which is very fast, but rational functions use divide, which is slow in a computer. So how does uh, this very beautiful method turn out with computation speed for the approximations?
Oh yeah, that's an interesting question. I haven't thought that much about the difference between a multiplication and division, but of course you're right. At some level, the division is much more difficult. Um, Not only that, right? Polynomials have the advantage, at least in Chebyshev form, you can use an FFT, right? Which is a really big advantage. Uh, so the fact that you're having a degree 20,000 doesn't actually mean you can't use it, right? For a polynomial. So I'm not looking to say that, oh, you should immediately stop using approximation tomorrow uh, and do this. But I think it's nice to be looking at this as an alternative in the future, particularly for problems where maybe you've got something evolutionary where often these singularities start to creep close to your interval or something like that, right? So yeah, it would be nice to avoid having to do it in a more expensive division, but that's beyond my pay grade, I think, at this point.
Thanks.